While I love my morning cup of coffee at home, I also love my morning cup of coffee at Wawa. Driving to work via stop at Wawa is a true delight. For those unfamiliar with Wawa, think of them as a really well-run convenience store with fresh food and cheap gas. For me, Wawa is one of my favorite companies to do business with. One of the appealing aspects of Wawa is their business model. It values the idea of building community. One of their mantras is, "At Wawa, we don't have customers, we have neighbors." In this video, we analyze a fictitious Wawa scenario where they are trying to build community among people who are slightly farther than walking distance, anywhere from 2 kilometers to 10 kilometers away from the nearest Wawa. As part of their outreach, they contact local app customers to enjoy a free coffee at their nearest Wawa and observe the number of these customers who actually visit the store for their free coffee. Of specific interest is the relationship between distance from the store and the probability that someone redeems the coupon. The theory is consumers who are closer to the store will be more likely to redeem their free coffee gift than consumers who are farther away, but Wawa seeks to quantify this relationship. The data. Data for this problem is available at this website and can be downloaded using Read CSV. Taking a look at the data, we see that distance, measured in kilometers, varies from 2 to 10, and it seems like more offers were made to closer customers. In terms of redemption rate, well, let's get a rough estimate by adding a column via mutate to see the redemption rate. And this shows us the probability of redemption, which does indeed seem to decrease with distance. We can create a simple but inefficient model. We use models to inject our domain knowledge into a problem and to measure our uncertainty. The simplest model we know might look at each of these 9 observations individually. Here is the generative DAG. Each of the 9 different distances gets a different theta, and essentially the various estimates of theta do not inform each other. They are independent. They don't borrow information from one another. So in this model, knowing the success probability for 4 kilometers does not help you estimate the probability for 5 kilometers. This is a problem in the sense that you have information about the structure of the problem that you are not representing in your model. The model is not as smart or efficient as it could be if you were to inject that knowledge into the model. Despite the limitation, running inference and then plotting gets us some output. The output is rough though. It suggests wide uncertainty bands, and its expected success probability for customers, say at 7 kilometer distances, is estimated higher than 5 or 6 kilometer distance customers. It's not quite right. While we obviously get a rough idea of uncertainty here, we can do much better with a model that smoothly refines the estimate of theta as distance increases or decreases. To make theta a function of distance, we use a linear predictor. Here is the code I use to get a linear predictor inside of my generative DAG.
cups of coffee waiting for you to come home. You knock on the door about 4:45. I wanna hug and kiss you and say
The linear predictor. Let's take a side trip to learn about linear predictors. Y equals alpha plus beta times x is the standard form of a linear predictor. You could add more explanatory variables, but we will keep it simple for now. Beta is the slope where for every unit change in x, we get a beta unit change in y. With just one explanatory variable, x, this is the slope of a line, and alpha is the intercept dictating the vertical level of the line. Notice that a line goes on forever in both directions. Hence, as long as the slope is not 0, the y value can be any number all the way from negative infinity to positive infinity. Transforming the linear predictor with inverse link functions. For our purposes, though, we want the linear predictor to map to values of success probability, which are restricted to be between 0 and 1. Whenever you want to restrict the range of a linear predictor, you should look for an inverse link function. The inverse link function I will use in this video is known as the inverse logit function. Let's not worry about that scary name, but rather understand it is some function that maps all values all the way from negative infinity to positive infinity, and it maps those values to other values which are restricted to be in the range you want. For us, the range we want is between 0 and 1. After all, we are modeling a probability that must be between 0 and 1. The particular inverse link function we will use here is called the inverse logit function. Its function is expressed here using theta to represent a probability, and y, the value of the linear predictor. So theta is a function of y. Here's a graph of the inverse logit function. So let's say our linear predictor spits out a value of 0. Then to convert that to a probability, you find 0 on the x-axis and see what probability it is mapped to. In this case, 50%. Negative 3 would map to about 5%, and say positive 1.1 maps to about 75%. Infinity for y means theta is infinitely close to 1, and negative infinity makes theta infinitely close to 0. The inverse link function can successfully turn any value from negative infinity to positive infinity into a value between 0 and 1. Using the inverse link function, we are about to estimate the alpha and beta variables of a linear predictor whose form is y equals alpha plus beta times x. Plausible values for alpha will be around negative 2.5 when we estimate it, and plausible values for beta will be in the neighborhood of negative 0.25. Thus, one plausible sample draw of alpha and beta might yield this formula for calculating a draw of our linear predictor. Y equals negative 2.5 plus negative 0.25 times x. We will have to manually code up the generation of a draw for the linear predictor. Since it is a deterministic function of alpha and beta, just plug in x and get a value for y. Graphically, this function of taking an x value and yielding a y value is just a line that looks like this when alpha is negative 2.5 and beta is negative 0.25. With linear predictor in hand and an inverse link function to use, namely the inverse logit, we can get to our ultimate goal of success probability. We plug in the value for y to get a value for our success probability theta. For example, let's say x equals 6. In our example, this means the customer is 6 kilometers away from the store. Based on alpha of negative 2.5 and beta of negative 0.25, this means the linear predictor takes a value of negative 2.5 minus 0.25 times 6, or that all equals negative 4. Our linear predictor being negative 4 can then be translated using the inverse logit function. We can see from this graph that negative 4 leads to a success probability around 1.8%. Now, the linear predictor and success probability are mathematically related. Given one, you can get the other. So while we understand changes in distance x having a linear effect on changes in the linear predictor, we need to have the computer help us visualize how changes in x actually affect success probability. As you can see here, the linear predictor and the success probability will both increase or decrease together. The only difference is that the success probability change is no longer linear. Notice the curve induced in success probability as a result of the transformation. As distance increases, the linear predictor decreases, and success probability decreases as well. Generative DAG with a linear predictor. With our aside on inverse link functions complete, we are now in a position to fully digest this generative DAG. The generative story is that we have some random parameters, alpha and beta, both with priors chosen to reflect our domain expertise. Alpha's prior is centered at -3, corresponding to a prior belief that a free coffee promotion should start with around a 5% success probability. And beta's prior is centered around 0 with a standard deviation of 3, suggesting that distance might have 0 effect, but could have dramatic effect as uncertainty of 3 for the standard deviation means the linear predictor can easily be swayed 3 to 6 units in either direction. We can have this broad uncertainty in standard deviation, as I'm confident we have enough data to narrow down this uncertainty quite easily. When alpha and beta get combined with a given distance, they provide a value for the linear predictor. The inverse logit then converts this to a success probability, which dictates the percentage of n offers that get redeemed. As we run Bayesian inference on this generative DAG, we will discover the alpha and beta parameters that are most consistent with our prior beliefs and the observed data. Let's see that by running DAG greta. The painful news. The big pain now is that DAG greta only gives us the posterior for alpha and beta. It is up to us and our coding skills to convert these posterior draws of alpha and beta into posterior draws of our parameter of interest, namely the offer redemption probability. The conversion turns out to not be that bad, except we are reliant on a given distance measure. Since we are interested in all possible distance measures, x ranging from 2 to 10, we can make a function that when given a distance, returns posterior draws of theta for that distance.
I'm a little like a link of chain, just a ring around another. Running in and out again. Fly me on a kite line, smiling like a gold mine. I don't need to pray.
Testing our function, we see that at 4 kilometers, somewhere between roughly 1.8 and 2.2% of coffee offers will be redeemed. Let's introduce the ggdist package to calculate and visualize intervals from posterior draws. It can make our life a little easier in getting a bunch of posterior draws visualized for different distances. It has a geom called stat point interval, which compresses this big purple mountain in the lower right into a nice line, reflecting the exact same information.
Just a little in the afternoon.
In the stat interval plot, I use the width argument to get my 90% credible interval, and the point is the median. Flipping this graph on its side, we can then explore how the interval changes with distance.
Make it so. Just a little in the afternoon to hold me like a mother. Hang me on the evening moon. Set me on a low one. Show me how to go one more. Never find
To fill in all the white space of this plot, I'll use a for loop to get a data frame of posterior draws for theta, given distances ranging from 2 to 10 kilometers in half-kilometer increments.
Well, I ain't got long, I leave for a day. And I never had a lot to say.
The effect of distance is now easily seen. At 2 kilometers, we are lucky to see 3% redemption rates, whereas at 10 kilometers, 1% would be an optimistic redemption rate. But the visualization makes it clear how quickly success probability for our offers declines as a function of distance.
Do we throw it all away? Sitting on the sideline, fooling with a fine line, never needed no desire. Go to the end.
Quick summary. So we used a linear predictor in combination with an inverse link function to allow a continuous explanatory variable, like distance, to inform our uncertainty intervals. Using our initial simple model left us with the credible intervals you see here. By introducing some domain knowledge, mainly that success probability should smoothly decline with distance, our uncertainty has been greatly reduced, and thus our ability to make decisions of this coffee promotion going forward will be of much higher quality and with much greater insight.